Welcome to This Explainer. If you've ever looked at a coordinate plane and just seen a flat, boring grid of abstract numbers, well, I really want to change your perspective today. Imagine for a second that the coordinate plane isn't just a piece of paper. Think of it as a massive, physical playground that we can actually explore together. And on this playground, straight lines aren't just equations, they're literally the roads we travel on.
Now, as we travel these geometric roads, we have to ask a few fundamental questions. Just how steep is a road? Is it going uphill or downhill? And if we've got two different roads, are they heading in the exact same direction, or do they intersect to form a perfect, sharp corner? These simple physical questions about our environment are actually the absolute core building blocks of understanding our entire mathematical universe.
To answer those questions, here's a quick roadmap for our journey today. First, we'll hit the math playground. Second, what is slope? Third, calculating rise over run. Fourth, parallel and perpendicular lines. And finally, number 5, the path to calculus.
All right, let's dive right into Section 1, the math playground, grounding abstract concepts in reality. So, if our lines are roads, what actually happens when two of those roads meet? Well, the exact point where they cross is called the vertex, and the space between them is what we call an angle. But an angle is really just a measure of turning. Imagine you're standing right there at that vertex, facing the flat horizontal road. If you turn your body counterclockwise, we consider that a positive angle of rotation. But if you turn clockwise, that's a negative angle. It's really all about the direction you spin. Now, if we take that idea of a positive turn and apply it to a single road rising up from the flat horizontal x-axis, we get what mathematicians call inclination. We represent this with the Greek letter alpha. Inclination is simply the exact angle, strictly measured between 0 and 180 degrees at which our metaphorical road is pointing. Think of it as the raw angle of a line's steepness.
Moving right along to Section 2. What is slope? Measuring steepness.
We all inherently understand the concept of steepness. Think about two actual slides at a playground. There's the one you gently glide down, and then there's the one that drops you terrifyingly fast. That physical steepness is what we call slope, and mathematics gives us a highly precise way to measure it using trigonometry. Slope, which we represent with the letter m, is mathematically derived from the tangent of our inclination angle, alpha. So m equals tan alpha. If you remember your right triangles, tangent is opposite over adjacent. In the context of our coordinate playground, that just means our vertical rise over our horizontal run. Which brings us to Section 3, calculating rise over run. Let's look at the actual mechanics of movement.
Let's break down exactly how we measure the steepness on our grid. You've definitely heard the iconic phrase, rise over run. Basically, our slope equals the change in y over the change in x. We use that little triangle, the delta symbol, to represent change in. So we're simply taking our vertical movement, how much we moved up or down on the y-axis, and dividing it by our horizontal movement, which is how much we move left or right on the x-axis.
What's really cool is that our entire universe of lines can be summarized into just 4 distinct types of slopes. As we move across our map from left to right, if our road goes up, we have a rising line with a positive slope. If it goes down, it's a falling line with a negative slope. A completely flat horizontal road, that has a slope of exactly 0. But wait, what if we have a vertical wall? Well, our horizontal movement, our run, is 0. And since we are never allowed to divide by 0 in math, a vertical line has an undefined slope. There's literally no numerical way to express it.
So how do we actually crunch the numbers and calculate this from two specific points on our map? We just follow 3 perfectly logical steps. Step 1, find delta y by subtracting our first y-coordinate from our second. That gives us our vertical change. Step 2, find delta x by subtracting our first x-coordinate from our second, giving us our horizontal change. And finally, step 3, divide that delta y by delta x. It's just a simple ratio utilizing the logic of vertical change over horizontal change. Okay, but before we go a single step further, I have to highlight a massive warning here. Calculating delta x over delta y is completely backwards. It is the most common mistake people make, putting the horizontal run on top of the vertical rise. You must always, always think y over x, up and down divided by left and right. Don't fall into that trap.
All right, Section 4, parallel and perpendicular lines. What happens when roads intersect? Or, well, don't.
When we put multiple roads on our coordinate plane, they interact in some truly fascinating ways. On the one hand, we have parallel lines. Think of railway tracks.
They have the exact same steepness, going in the exact same direction, meaning slope 1 perfectly equals slope 2. On the other hand, by contrast, we have perpendicular lines. These are roads that crash into each other to form a perfect right angle, a 90-degree corner. The math here is honestly beautiful. If you multiply their two slopes together, slope 1 times slope 2, it will always, without fail, equal exactly -1.
So the absolutely crucial point here is this. If two non-vertical lines are perpendicular, their slopes are what we call negative reciprocals. This simply means if one road rises quickly with a slope of +2, the perpendicular road must fall gently with a slope of -1/2. They balance each other perfectly, mathematically locking together to create that perfect 90-degree corner.
And this brilliantly illustrates the triangle example from the source text. Imagine 3 points forming a triangle, vertices A, B, and C. In step 1, we calculate the slope of side AB, which comes out to -8/7. In step 2, the slope of side BC is +7/8. For step 3, if we multiply them together, -8/7 times 7/8, the 7s and 8s completely cancel out, leaving us with exactly -1. This proves definitively that sides AB and BC are perpendicular, meaning our vertices form a perfect right triangle. How cool is that?
And that brings us to section 5, the path to calculus, the grand finale.
Now you might be wondering, why does all this matter for calculus? Why spend so much time calculating the precise slopes of basic, straight roads?
Well, because it's all part of this incredible mathematical evolution. We start with point 1 on our timeline, the simple physical concept of rise over run. That gives us point 2, the slope of a straight line. But the real universe isn't made of perfectly straight lines, right? It's made of curves. So in point 3, calculus actually takes our slope concept and applies it to a curve. How? By drawing point 4, a tangent line, a straight line that touches the curve at just one single point, showing its exact steepness in that freeze frame moment. And finding the slope of that tangent line, that brings us to point 5, the derivative. It's the ultimate tool for measuring instantaneous rate of change in the universe. To build that sturdy bridge to calculus, these are the 4 geometric pillars you absolutely must take away from this explainer today. 1. Slope is the tangent of the inclination angle. 2. Slope is the change in y over the change in x. 3. Parallel lines have identical slopes. And 4. Perpendicular lines have slopes that multiply to -1.
I want to end by reflecting on this really profound quote directly from the text. If you understand these 4 ideas geometrically, not just as formulas, you have the foundation needed to understand derivatives and rate of change later. Mathematics isn't just a list of random rules you have to memorize for a test. It's a deeply connected, geometric story. By mastering the straight lines of our mathematical playground today, you are profoundly equipped to explore the complex, curved universe of tomorrow. So the next time you look at a simple curve, ask yourself, how many infinite, invisible straight lines are hiding right beneath the surface?